Okay. All right, let's try it again. So we're going forward and we're throwing it back at the same time, right? We're talking about normal approximation to binomial distribution and to the p-hat distribution. Cool. All right. So the probability that a new vaccine will protect adults from cholera is known to be 0.85. The vaccine is administered to 300 adults who must enter an area where the disease is prevalent. What is the probability that more than 280 of these adults will be protected from cholera by the vaccine? This question falls into a category of a binomial experiment with the number of trials n equal to 300 and a probability of success p equal to 0.85, right? And the number of successes r is greater than 280. It is possible to use the formula for the binomial distribution to compute the probability of r is greater than 280. However, this approach would involve a number of tedious and long calculations. There is an easier way to do this problem. For the conditions stated below, the normal distribution can be used to approximate the binomial distribution, right? Hey. So normal approximation to the binomial distribution. Here's a source right here, right? So consider a binomial distribution where n is your number of trials, r is your number of successes, p is your probability of success on a single trial, q is your probability of failure on a single trial, which is also written as 1 minus p, right? This is key right here, right? This is important right here. If n times p is greater than 5 and n times q is greater than 5, then R has a binomial distribution that is approximated by the normal distribution with mu equal to n times p and sigma equal to the square root of n times p times q. Note, as n increases, the approximation becomes better, all right? So the key thing that we want to list here, right? You have to take your sample size, multiply it times your probability of success. I need that to be greater than 5. I don't care what the number is, as long as it's bigger than 5, right? I also need you to take your sample size, multiply it times your probability of failure. That's the 1 minus p, right? I need that to be also greater than 5. Both of these have to be bigger than 5 at the same time, right? And then, and only then, can I use this normal distribution to approximate the answer, all right? So
That is in chapter 4. That is in
7.
chapter 7.
7. We're still in
Yeah.
7 here.
I worked on that.
So let's look at an example. So binomial distribution graphs. This is telling us to graph the binomial distribution for which P, our probability of success, is 0.25, Q, probability of failure is 0.75, and the number of trials is first n equals 3, then n equals 10, then n equals 50. Let's take a look at what those look like. I could draw them out, but I don't feel like drawing them out because my handwriting is not too cute, and this computer does an amazing job, right? So let's look at this first figure, right? 731, right? This is for n equals 3, right? So our number of successes are what? 0, 1, 2, 3, right? And this is how our distribution looks. Now, it doesn't quite look like a normal distribution, like a bell curve, right? Because the n is so small. But look what happens when we increase the n just a little bit, right? So this is n equals 10, right? Now, this distribution starts to look a little bit more normal. It's not perfect, but it looks a little bit more normal. That's what I want you guys to see. Whenever I say normal, I'm kind of referring to this red line right here, right? I want the bars to just kind of fit almost perfectly under the red line, right? I don't want no yellow spaces or nothing like that, you know? I'm looking for like a perfect fit, all right? Now look at this one. This is n equals 25. That's what I'm talking about right there. You know, like that's almost perfect. See what I'm saying? Like almost right underneath that red line. And remember how we do these bars again, these histograms, right? For a binomial distribution, your R, your number of success, is going to be in the middle of the bar, right? So we're not really dealing with class width here. It's just in the dead middle, right? That's gonna come back to haunt us in a little bit. You'll see. Yo, take a look at this one now. This is n equals 50. Yo, this is popping right here, right? Like this is almost perfect. All right? Compared to the 25. Mm-hmm. It's all right. Wait till you see the example. The example is really easy. What's up, man? How are you? Good, good. All right. All right. So when n equals 3, the outline of the histogram does not even begin to take the shape of a normal curve. But when n equals 10, 25, 50, it does begin to take the shape of the normal indicated by the red curve. So from a theoretical point of view, the histograms in the figures would have bars for all values of r from r equals 0 to r equals n. However, in the construction of these histograms, the bar heights less than 0.001 unit have been omitted. That is, in this example, probabilities that are less than 0.001 have been rounded off to 0. Same thing as a table, right? Doesn't change. All right, let's look at this example here. So the owner of a new apartment building must install 25 water heaters. Damn, that's a lot of money. From past experience in her other apartments, oh, she rich. She knows that Quick Hot is a good brand, right? A Quick Hot heater is guaranteed for 5 years only. She definitely rich. But from the owner's past experience, she knows that the probability it will last 10 years is 0.25. Hey, so here's a question. What is the probability that 8 or more of the 25 water heaters will last at least 10 years? All right. Let's take a look at this. So I want to highlight some important stuff before I jump in, right? So she wants to install 25. That's an N. And then probability is 0.5, 25, excuse me. And you want to know what is the probability that 8 or more of the 25 water heaters will last? Sure. Like you want to see the top part? Oh no, I mean like right here. Okay. You're welcome. So I'm identifying some things, right? Like this is my N, this is my P, this is R. Okay. Good. All right, so I'm gonna use the approximation technique, right? So I want to know what's the probability of R, right? They said 8 or more, so what am I gonna write? Tell me. 8 is gonna be here, but what's the sign in the middle? Not times. It's an inequality. It's an inequality. Is it so it's less than? It is 8 or more means less than? What does 8 or more mean? Okay. Greater than, right? Oh, greater. So greater than or equal to 8. Right? But now this is a little bit different. Hold on. N is 25, P is 0.25. So watch what we could do. We could flip this from R to X. So this becomes X greater than or equal to 8. Right? Now, I don't know how to do this with an X distribution. I got to change this to a Z distribution, right? So this is going to become what? Probability of z greater than or equal to x minus mu over sigma. But wait a minute. Because I'm trying to use the normal distribution to approximate the answer. That's the lesson, yeah. But I have a problem though. What happened to mu? What happened to sigma? They didn't give me that in the question. Right? But you remember from the binomial distribution, right? Mu is equal to what? For a binomial distribution. Go ahead. Yeah. Not one. There's a formula for mu. So I'm throwing it back to chapter 6 right now. What was the formula for mu? Something simple, just two things multiplied by one another.
Mu equals E
Not E, the other one. This something similar. No, it's not similar, simpler. Yeah. In chapter 6. Mhm. It's something times something. NP, N times P. Very good. What about the standard deviation sigma? What's that? Chapter 6. Hmm. The square root?
yes.
Uh-huh.
E,
No,
sigma.
the other one, but below that. Huh? NPQ, right? So this is N times P, yep, times 1 minus P. Simple, right? Now you just plug in the numbers that we have above and that's it. All right, so let's do that. N times P, this is going to become 25 times 0.25, which is not 1. 25 times 0.25. What's that? All right. 6.25, right? Same thing on the bottom, nothing crazy. Square root, N is 25 times P 0.25 times 1 minus 0.25. What's that answer? So Q is 1 minus P, right? Yeah. It's on your formula sheet, it's right above it, says it. It's like real small though on the right hand side. Yeah, I notice how much I copy from the formula sheet. I'll make up none of this. Everybody's cool with typing this in the calculator, or y'all need to see it done? You good? All right. It's that time of year. And the farmer's market still ain't open up to sell my honey. No, you suck. Nobody with a calculator? I need square root 25 times 0.25 times 1 minus 0.25. What's that? That's true. And then square root that. Hold on. What you said? That's probably right. Yep, that's what I got. 2.165064. All right. Coming back to over here now, right? It's starting to look a little bit easier now, right? This is z greater than or equal to 8 minus the mean mu, which is 6.25, over the standard deviation sigma, which is the 2.165064. Right? Now we brought it back to what we were doing before. Now it's simple. This becomes probability of z greater than or equal to. All right. Just throw that in the calculator. Keep it simple. This is 8 minus 6.25 divided by whatever the standard deviation is, 2.16. And you get this, 0.80829. Now, if you're going to be using the formula sheet, which is an option, you got to round this off to 2 decimal places. So we got to look at the thousands place, and then consider what we're going to make the hundreds place. So in this case, if I'm rounding this off to 2 decimal places, this becomes probability of z greater than or equal to 0.81. All right. Questions on this? You good? Standard deviation, all that, yeah. The same ones from the homework, just copy and paste. Now remember, I can't look this up, this greater than, right? So I gotta make it less than. So this becomes 1 minus the probability of z less than or equal to 0.81. Remember, your formula sheet can only do less than, it can't do greater than, right? So this becomes what? 1 minus 0. Hey, what's good, man? How you doing, man? And then we just look this up. It says 0.81. As soon as I figure out where is my formula sheet, I had one. Yippee. So anyway, I'm looking up 0.81. Gonna go to the normal distribution table. Gotta turn the page till I get here. And I'm looking for positive 0.81. This is the negative side. Gotta go to the positive side. This is the positive side. I'm going down to 0.8. Then I look up top to where the 1 is. Here's the 1. Wherever they intersect that's my answer. So that's the 0.7910. Let's look at this. So the calculator. Final answer. Not bad, right?
You went to table 3, you went to 0.8, right?
And then up top is the 1. And I look at where they intersect though. I went to 3.
Did you go?
Let me see.
Oh, you went to 1.
Yeah.
You're one. You went to 1.
Yeah. Yeah, they're like where they came. So I got that number, 0.7910. So what did we do just here? Do right now, just here, right? Instead of using the binomial distribution to figure out this problem, right? We used a normal distribution to help us get this answer, all right? And we did that because our n over here is ridiculous, right? That's n equals 25, right? And then they want to know what's the probability of 8 or more. So when they say 8 or more, what are they talking about? The probability of 8, 9, 10, 11, 12, all the way up to 25. And remember, we had that probability, that, what's it called? Hold on. The binomial distribution. Let me just recap with y'all real quick. So remember, we had our binomial distribution formula right here. And remember, that formula was only good for one event, right? So that's like the probability of 8. I could use that formula to find it. Then I have to go back and do it for 9, for 10, 11, all the way up to 25. And then when I get all those answers, I add them together, right? By using a normal distribution, I'm skipping doing that. I'm able to use the normal distribution to approximate the answer, right? But for part B, how does this result compare when the result can be obtained using a formula for the binomial probability distribution? Let's answer this as if we were using the formula, right? Not going to use the formula. That's going to take too long. We're going to do this Danny style. All right. So I have my n. It's 25. My probability of success is 0.25. So I want to know what's the probability of r greater than or equal to 8. Once again, we know that that's going to be what? The probability of 8 plus the probability of 9 plus, skip a few, you get the idea, all the way up to the probability of 25, right? Now, remember, we can also do this in the calculator, right? To do this in the calculator, though, the calculator cannot calculate greater than or equal to. It only understands less than or equal to. So we can do the complement of this and say 1 minus the probability of r less than or equal to 7, right? So what is that? That's going to be 1 minus the probability of 7, put a bracket here, plus the probability of 6, plus, you get the idea, all the way down to the probability of 0. That I could do in the calculator, right? Let's do it. So this is going to become 1 minus our binomial CDF, where my n is 25. Trying to say that. And my p is 0.25. And my r in this case is 7. So that means I'm going to take all the numbers from 7 down. I'm going to add them together. So 7, 6, 5, 4, 3, 2, 1, 0. I'm going to add all those probabilities together to get this answer, right? But I'm not really interested in the less than. I'm interested in the greater than. So I have to do the complement by doing this 1 minus right here. So Carmen, you got to remember NPR on the bottom, right? These letters, NPR. That's what you got to remember for your calculator. But same order. And you're going to type it in just like that. Just like that. One second. All right, 2 more seconds. Hold on. Every time I open my calculator, I get pop-ups. Over here trying to sell me discounted World Cup tickets. I think the cheapest price I saw was like 10,000. I'm good. But that's not even the outrageous part. $150 to actually take the train over there. That's crazy. A little wind feel good, not gonna lie. All right. So I'm gonna type this in. This is gonna be 1 minus, now to get to binomial CDF, we're gonna go second distribution. We go down to our binomial CDF. Enter. Our trials, that's our N, that's 25. Our probability of success, P, that's 0.25. Distribution, DISTR. Yeah, then you just go down. If you have the 36X Pro, you're gonna press second data, then you're gonna go across the distribution, then you can go down. And then my X value here, we said was 7. And that's my answer. Say it again? Yeah, the same way. The same way it's there. Uh-huh. So it's 7 because the question wants 8 or more, right? We want R greater than or equal to 8, which is 8, 9, 10, 11, 12, etc., all the way up to the 25. But the calculator cannot calculate greater than, it can only calculate less than, right? So we do the complement, right? We do 1 minus the less than. So the numbers that I don't want are 7, 6, 5, 4, 3, 2, 1, 0. So I add up all of those and I just do the opposite of that. All right, and that's it. So this answer that I got right here, let's be clear about something. This answer that we got right here, like this is like the answer to the question. Like period. You know, like that's the real answer right there, right? But I'm interested in approximating the answer because I don't want to go through all this work, right? So I want to use a normal distribution to approximate it, right? So let's look at the answer that we got before. That's the 0.209. Okay. Not bad, right? When we did the normal approximation, it came out to 0.209. But the actual answer we got was 0.27349, etc., etc., etc. Right? It's okay. But to be honest with you, I feel like I could do better. Right? I feel like we could do better than this. All right. So here's something that you're missing, right? We have to correct, going back to our approximation over here, we have to kind of correct our assumption a little bit, right? So we're looking for the probability of the X greater than or equal to the 8, right? So the thing is that the 8 is good, but I could make it better, right? Imagine I had a distribution here where this is 6.25 and the 8 is somewhere over here, right? But remember that the 8 has like a rectangle about it, right? So what I want to do is I don't want to, for greater than or equal to, right? I don't want to just start from 8 and then go this way. I want to take it back a little bit. Just a smidgen, right? 0.5. Let's take it back by 0.5 just to encompass the whole bar of 8, right? Same thing with like the I'm about to say the confidence interval, but I mean to say the oh class boundaries. That's what I'm trying to say, right? Think of this as a class boundary for a binomial normal distribution, right? So what am I going to do here, right? If I'm taking it back, I'm going to take 8, I'm going to subtract 0.5 from it to give me 7.5, right? So now I believe that if I do the same question from 7.5, I'm going to get a better answer closer to what the real answer is down here. So let's try that out. Let's try that out. In the interest of time, I will do this part on the calculator just so you guys can see how to do the normal distribution on the calculator again. But anyway, right? Probability of x greater than or equal to 8. I'm going to do that correction, right? So it's going to become probability of x greater than or equal to 8 minus 0.5. This is going to become probability of x greater than or equal to 7.5, right? And then the rest of it is the same. All right, we're going to change this into a z. This is going to be x minus mu over sigma. Plug in the numbers. I'm sorry? So I'm trying to find a better approximation to the answer, right? So look, we got 209. 209 is good, but I'm saying that it could be better, right? So we're using a correction to make it better, right? We're subtracting 0.5 to make it 7.5. So now this is going to become 7.5 minus our mean, which we said was 6.25, over our standard deviation, which was, oh, I don't even remember what that was. That was something crazy. That was like 2.165. So let's get this, what am I doing? Let's get this answer right here. So this is going to be 7.5 minus the 6.25 divided by, where's that number? This number. Cool. Say it again. Sure, sure. So remember, I want two decimal places after the decimal, right? So I have to consider the thousandths place and then round off the hundredths place from that. I got 0.577, right? Yeah. So the thousandths place is a 7, so I'm going to make the hundredths place an 8, all right? So this is going to become 0.58. Now, I know y'all all know how to use a table. I want to show you guys with the calculator how to do this, right? So remember, whenever we're doing this in the calculator, we need to draw our distribution. All right, in the middle is always 0. All right, so I have a positive 0.58, so that's over here. And I want the area to the right of that, greater than, right? So remember, you always stand in the distribution. Right? Whatever is to your left, that's your lower bound. Whatever's here, right, that's your upper bound. This upper bound happens to be what? Infinity. Now, how do I write infinity in the calculator? This is going to be 1E 99. And after that, we get the answer. All right? So let's check it out. Let's look at how to do this on the calculator. Actually, wait, hold on. I should write more about that. For Carmen, this is normal CDF. They're going to ask you your lower bounds, comma, your upper bounds, comma, your mean, comma, your standard deviation sigma. All right? For us, that's going to be what? Normal CDF. What's my lower bounds? 0.58, excuse me. What's my upper bound? Infinity. That's going to be 1E 99. Mean is going to be, what's the mean always? Close. Give me the other answer. It's not 1, it's X? No, it's a number. For a standard normal distribution, the mean is always not 35. It's a real simple number. No, not 1. Give me something more simple than 1. 0, now we're talking. Right? What's the standard deviation? What is it? It's what you guys were saying before. What is it? 1, right? And that's it. And we type it in the calculator, click enter, and we're good. So let's take a look. Hey, what's up, man? All right, so for this, you go to second, you go to distribution. If you have the 36X Pro, it's going to be second data. Then you're going to go across the distribution. And you just go down to where it says normal CDF, and you click enter. Your lower bound is the 0.58. That doesn't sound right. Hold on. 0.58. That looks better. Your upper bound is infinity, right? So that's going to be the 1. But check this out. That E that's there is this double E that you see right here, EE. So you have to press second and then EE. Right? That's how you get that E there. And then 99. That E means times 10 to the 99 power. It's the largest number that the computer, the calculator understands. What happened? That's infinity. Yeah, so the calculator doesn't understand infinity, but the largest number that the calculator understands is this. So this is how we approximate it. All right? And then of course mean 0, summation 1, enter, 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 enter. Boom, that's your answer. All right? So this comes out to be what? 0.280 9572634. Yes, 99. Second EE 99. Go ahead. Theta. Like this. Yeah. So in trigonometry, that's an angle, right? For like an edge or something. Yeah. We don't. No. If you want to take calculus and come back to this subject, then I'll explain to you how we use it in this subject. Yeah, I got you though. Yeah. So now look, this answer that I got here, let's compare that to what the actual answer is. 0.273, right? I feel like this answer is a lot closer to what the actual answer is, right? This is a better approximation. So the lesson here is that you have to use this continuity, this correction, in order to get your answers here. And don't worry, you only have one question to do for the homework with this. So our first time without it, this wasn't so great, right? But with this is a good approximation. How you could tell if it's good or not, subtract the answer you got from the answer that the actual answer, right? You want to look at what that difference is. You want that difference to be as small as possible. Absolute value, of course. You want it to be positive, but you want it to be as small as possible. This answer that we did here with the correction is like 0.03 of a difference between their actual answer. Or is it 0.07? Hold on. 0.01. Even better, right? But this answer that we got here for the first time, this is like way off. This is like 0.07, right? So I rather be off by 0.01 than be off by 0.07. Right? Make sense? All right. Y'all got one question for homework, it's just like this. One itty bitty little question. So let's keep going. So remember that when we use the normal distribution to approximate the binomial, we are computing the areas under the bars. The bar over the discrete variable r extends from r minus 0.5 to r plus 0.5. This means that the corresponding continuous normal variable x extends from r minus 0.5 to r plus 0.5. Adjusting the values of discrete random variables to obtain a corresponding range for a continuous random variable is called making a continuity correction. All right. Those of you that's going to switch your major and take calculus, remember that. Continuity correction. All right. But you know I can't just leave y'all hanging like that. This is how to make a continuity correction right here. This is the sauce right here, all right? So how to make the continuity correction. Convert the discrete random variable r, number of successes, to a continuous normal random variable x by doing the following. If r is a left point, less than, right, of an interval, subtract 0.5 to obtain the corresponding normal variable x, that is, x is equal to r minus 0.5. If r is a right point, right, of the interval, my fault, left point greater than, right point less than, add 0.5 to obtain the corresponding normal variable x, that is x equals r plus 0.5. For example, all right, let's say I ask you what's the probability of 6 less than or equal to r less than or equal to 10, where r is a binomial random variable, right? Is approximated by, now look, you have r less than or equal to 10, right? So 10 is on the right-hand side, right? So you want to move that over. You're going to add, right, 0.5 to it for less than. But the 6 is greater than, right? So you're going to subtract the 0.5, right? And then that's how you get that, all right? So it's going to be 5.5 less than or equal to x less than or equal to 10.5, where x is the corresponding normal random variable. And that's it. Questions on this? Y'all will see it again for homework. Remember this, though. This will help you with your homework. It's only one question. Don't stress it. I just want to show y'all visually what this is. As you can see right here, I want from 6 to 10. So for the 6, I have to go over a little bit, subtract 0.5 to encompass the whole bar. And for the 10, I have to go over by 0.5 to encompass the whole bar. And then now, from 5.5 to 10.5, that is a better approximation, right, than just having the 6 to the 10. So that's the meaning of it. Yeah. You could use the binomial if you want, but the binomial is massive, you know? So this is an easier technique to get to the answer. Using one answer is an approximation and the binomial is the answer. Yeah. It's an option. It's an option, yeah. When n is too big, you don't want to use the binomial. You know? But if you have an n that's reasonable, like let's say 10, you could do that by hand. That's not too bad, you know. But sometimes it gets like out of hand. Go ahead.
What's the O code? Goes to line up the side.
Oh, sigma is standard deviation.
Just on the standard deviation.
And then just square it. Yeah, that's it. Or you just do whatever is underneath the radical and you call it a day. So you see your radical is like this, right? N times P times Q, right? Like this is sigma, right? Sigma squared is the same thing without the radical, N times P times Q. So you just multiply them 3 numbers together and just put it in and that's it.
You said don't use binomials for.
When n is too large, when your sample size is too large. Well, whatever you consider large. Your homework is 300. You know? Yeah. Yeah. Nah, like if we were talking about medicine, like let's say we're talking about the COVID vaccine, and it's 10,000. You know? Yeah. So we don't want to go through all those individual calculations one by one. So we want to use the normal to approximate it all. Yeah. I got you, don't worry. Because you want to know what it means, right? So let's look at this, right? What does a normal approximation to a binomial tell us? A normal distribution can be used to approximate the probability of R successes out of n binomial trials. In order to use a normal approximation, the products of n times p and n times q must both exceed 5, where n is the number of binomial trials, p is your probability of success on a single trial, and q your probability of failure, which is 1 minus p. Unless n is fairly large, a continuity correction may be necessary in order to improve the approximation. That's it.
That's it. All right, we got it.
In tutoring, we'll go over it. It'll make more sense. I got you.
Now, what is the final?
That's a good question. I don't know. It's probably, and I'm just guessing here. Don't quote me on this. I have to look it up. If I had to bet, I bet you it's the 21st. Yeah.
And this is gonna be over here. You sure, Mr. Lee? Right.
So
No.
sampling distributions for proportions. Let's continue. So in this section, right, we studied the sampling distribution for the mean. Now we have the tools to look at sampling distributions for proportions. Suppose we repeat a binomial experiment with n trials again and again, right? And for each n trials, we record a sample proportion of success, p hat, right? This is a new thing, p hat equal to r over n. R is your number of successes, n is your sample size, right? That's how you get that. The p hat value forms a sampling distribution for proportions. Okay? This is going to be something real cool. When y'all get to the 4-year school, y'all could look back at this and be like, oh yeah, I heard about this before. All right? So here we go. Here's the sauce right here. So sampling distribution for the proportion, right? P hat. So P hat is equal to R over N. Remember, R is your number of successes, N is your sample size. Given N is the number of binomial trials, a fixed constant, R number of successes, P probability of success on each trial, Q is equal to 1 minus P, which is your probability of failure on each trial. This is important. If N times P is greater than 5 and N times Q is greater than 5, then the random variable P hat R over N can be approximated by a normal random variable X with mean and standard deviation. So here we go. The mean for P hat is going to be equal to P, whatever R over P is. The standard deviation for P hat, though, is the square root of P times Q over N. Cool, 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 cool. Let's make a comment. Say it again.
I know that.
Yeah.
So I do find a standard deviation
Mm-hmm.
and square with the number, different time, but that's.
Just write everything. Sometimes the computer's real sensitive and it wants to see all the numbers.
Now, I was saying that because earlier, I used to be right all the time.
I wrote some of them, but I did use all of them in my calculation, right? Because I did it in Excel and then I just copied the cell into the formula. Yes. But yeah, if I'm writing something on paper, I might round it off to 4 decimal places or something. But in my calculation, I always use all of the decimals. Always, always. All right. Let's make a comment real quick. So to obtain information regarding the sampling distribution for the proportion P hat, which is equal to R over N, we consider the sampling distribution for R, the number of successes out of N binomial trials. Earlier, we saw that when N times P is greater than 5 and N times Q is greater than 5, the R distribution is approximately normal, with mean mu is equal to N times P and standard deviation sigma is equal to the square root of n times p times q. Notice that p hat is equal to r over n is a linear function of r. This means that the p hat distribution is also approximately normal when n times p and n times q are both greater than 5. In addition, from our work in the last section, right, with linear functions of random variables, we know that mu for p hat is equal to mu for r hat over n, which is equal to n times p, which is just equal to p. And the standard deviation for p hat is going to be the standard deviation for r over n, which is the square root of n times p times q over n, which becomes the square root of p times q over n. Although the values of r sat over n are discrete for a fixed n, we do not use a continuity correction for the p hat distribution. Hallelujah. This is the accepted standard practice for applications in inferential statistics, especially considering the requirements that n times p must be greater than 5 and n times q greater than 5 are met. We see from the sampling distribution for proportions that the mean of the p hat distribution is p, the population proportion for success. That should be rho then. This means that p hat is an unbiased estimator for our population parameter, whatever, rho. So what does p hat sampling distribution tell us? Consider n binomial trials where the p hat is equal to r over n to estimate the p for the population proportion, the population probability of success on a single trial where r is the number of successes out of n binomial trials. To create a p hat distribution, repeated sets of n binomial trials must be conducted to determine the individual sample statistic p hat. Fortunately, mathematics can be used to obtain the following information. For n times p greater than 5 and n times q greater than 5, the p hat distribution is approximately normal. Hallelujah. The mean of the resulting p hat distribution is rho, yay. The standard deviation, also known as a standard error, is the square root of p times q over n, where q is equal to 1 minus p. Yip-de-doo. All right, let's go to an example. The theory is fun, but the examples are more fun. Mm. I know that sound all too well. No, that's not a fire drill. No. Y'all know nursing is a hard ass major over here, right? All right. They trying to break into their room so they could see their test beforehand. That's all that is. You know, I ain't even mad at them. That's why I'm not going to go look, because I ain't see nothing, I ain't hear nothing. If y'all want to rat them out, go ahead. All right. Just bear with me 1 second. Just want to get all of the question up in there, you know, and then we could go through it. All right, I think we're good. We're good. All right, let's knock this out real quick. All right. So sampling distribution of p hat. The annual crime rate in the Capitol Hill neighborhood of Denver is 111 victims per 1,000 residents. All right. Ooh, how about them Denver Nuggets? Y'all seen that fight? Oh, y'all don't even know what I'm talking about. Dang, that fight was crazy, right? All right. So this means that 111 out of 1,000 residents have been the victim of at least one crime. That's where you can look it up. For more information, visit the website, blah, 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 or whatever. These crimes range from relatively minor crimes, stolen hubcaps, purse snatching, all the way to major crimes like murder. The Arms is an apartment building in this neighborhood, right? That has 50 year-round residents. Suppose we view, excuse me, suppose we view each of the n equals 50 residents as a binomial trial. The random variable R, which takes on the value 0, 1, 2, 3, 4, all up to 50, represents the number of victims of at least one crime in the next year. Here's the first question. What is the population probability, P, that a resident in the Capitol Hill neighborhood will be a victim of a crime next year? And what is the probability, Q, that the resident will not be a victim of the crime? I gotta highlight it. Let's see what we got here. So 111 victims per 1,000 residents. We have 50 year-round residents. N is equal to 50. All right. And R represents the number of victims, at least one crime in last year. All right. Simple question. What's the probability of a resident experiencing one crime? How you spell crime? C-R-I-M-E. Okay. Yeah, ever since I lost the 5th grade spelling bee, that was it. Gave up on spelling. Yeah. So what you guys think? It's a real simple answer too.
P plus prime.
Huh?
P plus prime.
P plus prime? Kind of. Let me give y'all a hint. It's P hat, which is equal to R over N. So what's the answer? What's R? What's N? Don't overthink it.
With the probability, you know. Are we using probability for something?
Not really. Just P hat. Maybe that's confusing.
The letter, do you think so? The answer?
It's a fraction. It's a number over a number.
Oh, 1 over 1.
But not this one, not the other. Yeah.
The P hat, yeah.
There's a P in there. You know, when you say.
Oh no, we're not there yet. I know what you're talking about. That's the next question.
They don't know it, but they don't know.
So in Denver, how many people experienced the crime?
But that's what I'm talking about.
111, right? How many residents are there? That's the answer. We done.
I was close, I say 1.
So now here's my question, right? What's Q? If this is P, what's Q? 1 minus. Y'all can really just copy from the formula sheet. Q is 1 minus what? No. Oh yeah, it is. It is actually that, yeah. But I'm looking for the letter first though. 1 minus P, right? So this becomes 1 minus, what's P? 111 over 1,000. Little bit of math, you get the answer, right? I don't even know, what's this gonna be? 1,000 over 1,000.
1,000.
Yeah, the Q formula, yeah. Yeah, what's 1,000 minus 111? You don't know? No. Like if you have $1,000 and you spend 111, how much you have left? Hmm? 35?
How can you say one and that is?
If you have $1,000,
889.
Oh.
Bad things, Just,
and there we go, that's Q. All right, so that's it for A. A was to find P and to find Q. There you go. All right, take a minute. So this is for A. They want to find P, then find Q. Simple, simple, simple. I'm gonna change my color for the next question. How about blue? You don't need to change this into a decimal. You could leave it as a fraction. I'm happy with fractions. I like fractions. All right. Look at this next question. Consider the random variable p hat is equal to r over n, where it's going to be r over 50. Can we approximate the p hat distribution with the normal distribution? Explain. All right. Forget that top portion, right? Can we approximate the p hat distribution with the normal distribution? What are they asking you? All right, here's what they're asking you. Remember what I was telling you before, right? N times P has to be greater than 5, right? And N times 1 minus P, or N times Q, has to also be greater than 5, right? In this question, they're asking you to prove that, right? So our new N that we have here, this is 50. And we're plugging in our P, which is the 111 over 1,000. And I want to know, is that greater than 5? I don't know, right? And we're going to do the same thing on the other side. This is our 50. And then we're plugging in our Q, which is 889 over 1,000. And my question is this greater than 5? All right? Little calculator, let's do it. What's 50 times 111 over 1,000? I don't even know. What's 50 times 111 over 1,000? I just figured it out in my head. But still, y'all should do it on the calculator. I really got to talk to these maintenance people. Like, it is 5:30. Why are you still cutting grass? Like, you know.
That's something in the.
Yeah.
Yes,
You know what I think they do? I think they cut like a little small portion just to show that they're doing work, and then they take a lunch break, and then at the end of the day, they finish the job. Mhm. Yo, they milk the clock real over here. Like real. Yo. Right? Like, yo, it just grew back in an hour. Like, I can't explain it. Like, all right, I did the first one, right? In my head. This is 5.55, right? Which is greater than 5, right? So we good. What about the other one? This is 50 times 889 over 1,000. What's that? Yeah, I just did it in my head. Yeah. Well, I knocked off a 0 off of 50 and knocked off a 0 off of 100. And then 5 times 111 is 555. And then it's divided by 100, so just move the decimal 2 places. So 5.55. But I can't do that in the next one, though. That's a big number.
Well, the thousand.
Oh, yeah, that's a big number. Yeah.
What is it now?
Yeah.
Word.
So we got 44.45 on the other side. Yes, that is bigger than 5. So here's a question, right? Can we approximate the p-hat distribution with a normal distribution? Yes, we can.
Yes, 5. 44.5, right?
Or you could say because this and this
Oh,
are greater than 5.
yeah.
All right? Keeping it simple. All right. Right. The next question is what you were asking about, the sigma and the mu. So we're gonna do that real quick. That takes like 2 seconds. That's what this is leading to, yeah. I want to. I hope so. I hope. Yeah. That would be mad relaxing. Yeah, that'd be mad relaxing. Just a whole bunch of data, just click, 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 done. You know? Yeah.
Who's saying that you're saying that?
The mu and the sigma. But it's mad simple though. Everybody done copying? I can do the last question. All right. So last question is mad simple, right? What is the mean? What is the standard deviation? Light work, right? All you gotta do is just copy from your formula sheet and you're done with the question, right? So let me take a look at my formula sheet. I gotta find it though. Where'd I put my formula sheet? All right, here it is, right? Whoops, I'm going the wrong way. Going the wrong way. So we in chapter 7. Here's my mean. Here's my standard deviation. Easy. Huh? The mean? It's just P. Yeah, that's it. Mm-hmm. So your mean for P hat is just the 111 over the 1000. You're done, right? Your standard deviation for the P hat is the square root of P times Q over N, right? Just plug it in. You already know what the answer is. It's square root 111 over 1000 times the 889 over 1000, all divided by the N, which is 50, and we done. Rest of that is calculator. Go ahead. The carrot, because it's P hat. That's what it's called. It's P hat. It's the probability of success from the binomial distribution. Yeah, that's just how they. And chapter 7 at the bottom. Chapter 7 in the bottom. Like the last 2 formulas, yeah. And then real quick, let me get this answer. Oh my God. I don't even know how to type this in. 111 divided by 1000 times, this is like 889 divided by 1000. Oof. Damn. It be like that sometimes. Let's see if we get it now. No doubt. Then divide by 50. Whatever. So here's my answer. 0.044425. I know y'all could do it in your calculator, so I ain't even stressing that. No questions on this? All right. Y'all got 5 minutes. Log into WebWork and do your homework. It's only one question, so y'all can do it. Mm-hmm. Mm-hmm.
But. I don't know if I got the wrong one.
I have a few videos I haven't posted yet, but I'm gonna do them tonight. Okay. Not necessarily. So do second with, right? Open parentheses and then open parentheses. 111 divided by 1000. Close parentheses times parentheses. 889 divided by 1000.
No?
Sorry.
Close parentheses, right? Then close parentheses one more time, right? So that's the numerator, divide 50. Close parentheses.
Oh, okay, I see.
Yeah,
Yeah.
that's it.
Thank
You're
you.
welcome.
Hmm.
So yeah, come up, sign the sign-in sheet, all of that. Start your homework. It's one question. You can finish it before class ends. Hmm? Can I take this down? Can I take this down?
This thing.
It's cool. I can take this down. All right.
That's all I'm saying.
Oh, okay.
Mr.
Uh-huh.